Welcome to The Explainer. Today, we're diving deep into the invisible, kind of mind-boggling choreography that actually makes your everyday devices function. Whether you're just scrolling on your phone, running heavy data models, or opening up a web browser, there is this massive, hidden dance of data happening right beneath your fingertips.
It really is a fascinating paradox, right? Just ask yourself, how exactly can a single machine seamlessly play your music, download some massive file in the background, update your apps, and instantly respond to your keystrokes all at the exact same time without just completely crashing? I mean, it feels like magic, but as we're going to see, it's actually an incredibly intricate system of task management.
To set the stage for this whole explainer, we really need to look at this absolutely brilliant quote from computer scientist Rob Pike. He hit the nail on the head when he said, "Concurrency is about dealing with lots of things at once. Parallelism is about doing lots of things at once." I really want you to keep this conceptual anchor in mind as we go. There is a subtle but absolutely critical difference between dealing with something and actually doing it.
All right, Section 1, hitting the speed limit.
So, to understand why these concepts even exist in the first place, we kind of have to travel back in time a bit and look at the physical limitations that literally forced computers to evolve. For decades, the industry basically relied on something called frequency scaling. From the mid-'80s on, if you wanted to make a computer faster, you just cranked up its clock frequency. Pretty simple, right? But around 2004, the industry hit a brick wall, the power wall. Pushing processors to higher and higher frequencies generated way too much heat and sucked up way too much power. Major chip manufacturers actually had to scrap development on some of their ultra-fast processors because they would quite literally overheat. You could practically fry an egg on the motherboard. Computers just couldn't get any faster doing one single thing sequentially.
So the hardware industry had to pivot, and fast. The solution wasn't to compute faster anymore. It was to compute differently. And that kicked off the multi-core era. Instead of one ultra-fast central processing unit, chips started getting built with multiple, slightly slower units, or cores, working together. But there was a massive catch. This hardware revolution completely upended things for software engineers. They had to redesign how programs were written from the ground up. Sequential programming was out, and parallelization was officially in.
Okay, Section 2, Concurrency versus Parallelism.
Figuring out the exact difference between these two is, for sure, the most common point of confusion in modern computer science. So let's ground these abstract ideas with a super relatable real-world analogy. Imagine a grocery store. Concurrency is like having a single cashier who is just unbelievably fast. They scan one item for customer A, instantly pivot to scan an item for customer B, then jump over to customer C. They're rapidly switching between tasks, making progress on all of them in overlapping chunks of time. It creates this awesome illusion of simultaneous action, but in reality, they're just context switching at lightning speed. Parallelism, on the other hand, is like having multiple cashiers serving multiple customers at the exact same time. It is truly simultaneous execution.
Let's break down the technical side of this. Concurrency can actually run on a single processing unit by using that interleaved context switching we just talked about. Because tasks are constantly interrupting each other, the order they finish in is unpredictable. In computer science, we call that non-deterministic. The main goal here is decreasing response time, making sure no single task ever gets completely blocked. Parallelism, though, strictly requires multiple processing units to pull off truly simultaneous execution. This makes it deterministic or highly predictable. Its main goal is increasing overall throughput, basically just getting more total work done faster.
Moving on to Section 3, Divide and Conquer.
So how do software engineers actually put these concepts to work when processing massive amounts of data? Well, when you're dealing with immense data sets, you need a very specific design pattern. Enter MapReduce. It's widely considered the hello world of big data, and it's practically a perfect example of concurrent design. It's a programming pattern that takes large data sets, splits them into independent chunks, which is the map phase, processes them all independently, and then aggregates the final results together. That's the reduce phase.
Let's walk through how this actually works. Imagine your input is this massive, chaotic stream of different vehicles. Buses, cars, trains, the whole shebang. Reading them one by one would take forever. MapReduce steps in and first splits this huge input up into smaller batches. Then, mapping nodes take those batches and start sorting them totally independently, picking out the buses, the cars, and the trains in their specific little chunk. Finally, the reducing nodes collect all these intermediate results and combine them into a beautifully organized, perfectly clean output of counted vehicles. It's brilliant.
Now, let's look at a motivating, real-world problem.
Say you're asked to find the closest Starbucks to your current location. Easy enough, right? But the data you're given is a massive 1 terabyte text file packed with millions of unstructured GPS coordinates and site names. If a single processor tries to read that file sequentially, line by line, you are literally going to be waiting hours just to get a cup of coffee. No way!
To fix this, we use our divide and conquer strategy. The system takes that massive terabyte file and chops it into tiny, manageable chunks. By chunking it up, we can unleash thousands of independent mappers to search through different pieces of the data concurrently. So instead of one tired cashier looking through a million receipts, we've got thousands of cashiers rapidly checking a few hundred receipts each. It drastically slashes the time needed to find that coffee shop.
Another really excellent example of this from our sources is Java's fork/join framework. It operates on that exact same divide and conquer principle. If a task, let's say summing up a totally massive array of numbers, is just too large, the framework recursively splits it into a left and right subtask. It forks these tasks out for parallel execution across different threads. Then, once the tasks are finally small enough to compute easily, it joins all those answers back together. It's a super elegant, highly optimized way to squeeze every drop of performance out of multi-core processors.
All right, Section 4, the race condition danger.
Now, all this incredible processing power definitely comes with some serious risks. Concurrent programming is notoriously brutal to write and honestly even harder to debug. Take the classic high-stakes bank deposit scenario. What actually happens if two completely independent servers try to deposit $10 into your bank account at the exact same millisecond? If the system isn't coded with absolutely flawless concurrency, the results can be pretty disastrous.
Let's step through the exact timeline of a failure known as a race condition. Step 1. Server 1 reads your account balance. It sees $0. Step 2. Because they're operating concurrently, Server 2 also reads the balance before Server 1 has finished doing its thing. It also sees $0. Step 3. Both servers independently do the math. 0 plus 10 equals 10. Step 4. Both servers write their result back to the database. The final balance, $10. Not the 20 you actually deposited. Because of those overlapping reads and writes, $10 just literally vanished into thin air.
To stop this catastrophic race condition from happening, software engineers have to build in very strict synchronization protocols. The most common fix is using what we call locks. A lock ensures mutual exclusion, which basically just means only one thread can access a shared resource, like your bank balance, at a single time. Server 1 locks the account, does the math, updates the balance to $10, and then unlocks it. Only then can Server 2 read the new balance of $10, add its own 10, and write 20. But you gotta be super careful here. Relying too much on locks can lead to deadlocks. That's where two servers basically just stare at each other forever, waiting for the other one to unlock a file. You can also cause a parallel slowdown, where the overhead of them trying to communicate actually makes the program run slower than if you had just run it sequentially in the first place. Crazy, right?
So, as we wrap up this explainer, I want to leave you with a final thought. We rely entirely on this massive, totally unseen architecture. The next time you open an app, stream a video, or check your bank account, ask yourself, how many invisible cashiers are rapidly switching tasks and juggling your data right at this exact moment? It's a complex, beautifully orchestrated concurrent dance, and we're all stepping to its rhythm every single day. Thanks so much for joining me on this deep dive.